Right, let's get started. Welcome to the session on designing functional programs. We're going to talk about some of the reasons to use functional programming just a little bit, and along the way, we'll talk about how practically we can get to designing systems with functional style of programming. Well, a lot of us, in fact, I would argue most of us in the industry have been building systems with two different programming models, somewhat mixed with each other. And if you really broadly look at what we have been doing over the past a few decades, I would say we've been programming in object-oriented programming, but that's not entirely true. Our objects contain methods, and methods contain code that executes certain instructions. And sometimes even outside these methods within each objects, we have methods that work with multiple objects. So pretty much what we can sum up this to is we've been doing imperative style plus the object-oriented style of programming in large. So we have not really been programming object-oriented entirely. It's been a combination of imperative and object-oriented for most part. But moving forward, though, most of the mainstream languages now implement some kind of a functional style of programming. Even languages like C++ have lambda expressions in them. We could use this in Java, we could use in C#. So there are so many languages that support functional style of programming. Well, then maybe we should reconsider why we should do this and why we should employ some of these things. Well, one of the reasons is the imperative style of programming is inherently more complex. On the other hand, the functional style of programming, even though it's not very familiar to a lot of us, actually gives us a lot better way to do things. It reduces the complexity quite a bit, and that's one of the biggest benefits we get out of it. So in that regard, let's talk a little bit about the functional style of programming. Well, functional style of programming has been around for a very long time. In fact, it's been around even before the time of object-oriented programming. And it's taken all these years to really get excited about it. And finally, there's a chance for us to use it because mainstream languages support it, like I mentioned. But one of the things about functional style of programming, as you learn functional style of programming, the very first thing people will tell you, including myself, is that we should favor assignmentless programming. So what in the world does it mean, assignmentless programming? Well, it means you will not make any assignments at all. In other words, you will not change anything at all. And you may wonder and say, gosh, is it even possible to create a program where nothing ever changes? I'm going to show you a program where nothing ever changes. And here it is, right there. And, well, it doesn't do anything also. That's one little small problem. But practically, though, is it even possible to create a program where nothing ever changes? Well, so the question is, what about assignmentless programming? That seems like a weird idea, isn't it? I want to draw some analogy to this before we go forward. Let's go back to years in the past. Let's say I want to create a Java program, and I'm going to put a blah in here. Now, notice the error that Java gives you. Java says, error, not a statement. I want you to remember that, not a statement. Okay, great. Blah is not a statement. That's kind of obvious. I'm going to say go to. Well, shouldn't it say not a statement? But when I run this code, well, the compiler tells me illegal start of expression. What does that mean? It means goto is actually a keyword in Java, and I dare you to use it. That's what they are saying. So we're not supposed to use goto, but it's a keyword in the language. But why? Because we know one thing. Remember good old Dijkstra. Edgar Dijkstra said, goto is evil, we should not use it. And so we all know we should not use goto. So we can say in here, goto is to structured programming, and leave it at that. We'll come back to this in just a few minutes. So we know not to use goto. But wait a minute, though. Let's quickly take a look at something. Int I equal to 0, I less than 5, 10, I plus plus. And I'm going to say if I is less than 5, then I want to output I. Rather a trivial program. Well, we know this is a structured program, isn't it? It's a structured program. Why? Because it's nicely structured. There's an input, there's an output, and there's an entry point and exit point. And of course, you don't jump around anywhere you want to. It's structured. Well, okay, so we know this is a structured program that looks really nice, but let's take a look at this real quick. Let's take a look at what Java really did under the hood. So Java P minus C Minus C is already an alias on my machine for Java P, so I won't use it right now. And I'm going to say class is sample.class and take a look at the bytecode real quick. And when you look at the bytecode, there's a bit of a surprise in there for us. And what do you see inside? Oh my gosh, there is Go to. Well, wait a minute, didn't we all agree we shouldn't use Go to? Well, Go to is like matches. I know you all have matches at home, right? But you don't go to children and say, children, I'm going to go take a shower. Here are some matches for you to play with. I hope you don't do that. Well, the point really is you have matches, but it's for adults to use. Exactly the point. So we don't want children to be playing with it. We want adults to be using it. So what I mean by that is just because we say no Go to in structured programming, it doesn't mean no Go to. It simply means there's no Go to in our code, but there could be Go to in layers below. Exactly the point about assignmentless programming also, and Go to is structured programming as assignment is to functional programming. And this is one of the main ideas to keep in mind is that when we say assignmentless programming, it doesn't mean there are no assignments. It simply means there are no assignments in our code. So there could be assignments in layers below. You say, wait a minute, if there are assignments in layers below, would it still be functional programming? Well, wait a minute. If you do assignment, what happens? If you do assignment, the code becomes hard to reason. The code becomes hard to maintain. The code becomes hard to understand. The code becomes hard to explain. The code becomes really hard to debug. The code becomes hard to make concurrent. All of these problems come in if you start mutating in your code. But what if the mutation happens in layers below? Well, every one of the problems I just mentioned becomes their problem and not yours. And in life, you always want to make things other people's problem. So you don't have to worry about this. So that's one of the really nice things is we delegate this to a lower level. So our code doesn't do any assignment. So one of the key things to keep in mind when it comes to functional programming is it's assignmentless programming. But I often use the word no explicit assignment. So what we mean by no explicit assignment is we don't do assignments, but assignments may happen in layers below, and we don't have to worry about it. So when it comes to functional programs, we favor immutability. So what does it mean to favor immutability? We don't do state mutation. Instead, we do state transformation. So rather than taking an object and changing its state, we make copies of objects in a prudent way, and there are efficient ways to do this. And then we make copies of it in a tactical way so that we don't waste memory. At the same time, we're not changing the state of objects. Well, the second thing about functional programming is it uses what are called higher order functions. So what in the world is a higher order function? Well, a higher order function simply is, well, think about regular functions, if you will. So what does a regular function do? May pass an object to a function. So we may pass an object to a function, and then we also may create object in a function, and then finally may return object after all, from a function. So this is what a regular function is. We may pass an object to a function, we may create an object within a function, we may return an object from a function. Now let's talk about the so-called higher order functions. So in higher order functions, we're going to treat functions as first-class citizens. We may pass a function to a function. We may create a function within a function, and we may return a function from a function. So this is what makes a function a higher order function. So when it comes to a regular function, we may pass objects around, we may create objects, we may return objects. When it comes to a higher order function, we may pass a function, we may create a function, and we may return a function. So what this gives us an ability to do is not only do object decomposition, we can also do functional decomposition as well. And as a result of that, all of a sudden, we can not only do imperative plus object-oriented, but we can do functional plus object-oriented. But if you ask me, my problem is not with object-oriented programming. I actually like object-oriented programming. I don't want to throw the baby with the bathwater and say, don't do this. Well, there are good parts of object-oriented programming and there are bad parts of object-oriented programming. But we can take the good parts of object-oriented programming, and where the imperative style makes it really hard, we can replace the imperative style with a functional style of programming. So as a result, we could mix functional and object-oriented to a healthy dose rather than suffering with the imperative style of programming. And that's one of the things we can do almost in any language today. You can do this in C#, you can do this in Java, you can do this in JavaScript. Keep going. There are so many languages in which you can actually do this pretty effectively. So you get the best of both worlds. You can write functional code plus object-oriented code to achieve your results. This is where higher order functions really come in. Well, but I want to really know how it feels to use and what is the difference between those two. To understand this, let's take a look at an example real quick. Let's say we have a list of numbers 1 to 10, and I'm going to say find the double of, let's say find the total of double of even numbers. That's what I want to find out. How do you do this in the imperative style of programming? You first say result is equal to 0, right? That's the very first step you do. And then you want to eventually print the result when you're done, but then you say for int element coming from numbers. And then you would say if element mod 2 is equal to 0, then you would say result times plus is equal to element times 2, and you perform this operation. This is, of course, we know as imperative style of programming. So what is imperative style? Like I mentioned earlier, you tell what to do and also how to do it. That is imperative style of programming. Anyone who has written code like this before? Every one of us, isn't it? But the more important question is, how do you feel when you write code like this? Real dirty, right? When you go home in the evening, you feel dirty. Children come towards you and say, hey, you're back from work. You say, don't touch me. I have to go shower first, right? That's how we feel. It's like we feel dirty. This is low-level coding stuff we have to do over and over and over. But thankfully, we don't have to do this. So that is imperative. And in the imperative, you tell what to do, plus also how to do it. But let's change the story here. We want it to be declarative and functional. Tell what and not how. So you want to tell what you want to do, but not how to do it. So what am I going to do in this case? I'm going to now start out and say numbers.stream. And I'm going to start with a stream. A stream is an internal iterator. And then I say filter, given an element, give me element mod 2 is equal to 0, only true, then give me the value, otherwise not. Perform a map to, in this case, we'll ask it to map to int. Given an element, give me element times 2, then we'll perform a sum operation, and then we are simply done with it. And if you notice, the result of this code is also the same value of 60. But this is a declarative style of programming. Let's understand what we are doing in this code. If you look at this line of code, this is declarative. Why is it declarative? Because you tell what and not how. On the other hand, when it comes to functional code, so I'm going to say functional is declarative plus higher order. So you're going to mix these two together to get your functional style code. And that's exactly what we're going to do here in this example. Notice that the sum was declarative. But what about this line? This is functional. Why is this functional? Because notice map to int. You tell what to do. You didn't tell it how to do the mapping. However, to the map to int function, you are passing another function as an argument. So that makes map to int a higher order function. Sum is a regular function and it's declarative. Map to int is a higher order function and it's declarative. It's higher order because we are passing a function as an argument to this other function. Likewise, we know that filter is functional as well. So all declarative code is not functional, but all functional is declarative. And that is one of the biggest benefits we get out of this is expressive power of the code. But where does this take us from here on? Well, where it takes us from here on is a very beautiful, elegant syntax that we can use in reality. Let's look at the beauty. Let's look at the elegance for a second before we go further. So I'm going to start with a create person over here, and this is going to create a collection of people and give it to us. So here's a collection of people objects. What I want to do here is I want to say get the names of names in uppercase, let's say, of people, let's say in this case older than let's say 30. So how do I get the names of everyone who's older than 30 in uppercase? Well, I don't want to write the imperative code because everyone knows there is imperative style and how we can write it, but let's write the code in functional style. So I'm going to say over here, first of all, output. Well, I want to put it into a collection. How about that? So we'll say names, but I want the names collection. So list of string names is equal to, and I'm going to start with create people dot stream. And once I get a stream out of it, I'm going to say filter, given a person, give me a person dot get age is greater than 30. But I don't want the person, I want the person's name. So map person, in this case, I'm going to say get name. But I don't want the name, I want it in uppercase, string to uppercase. But I don't want the names alone, I want it in a list. So collect to list. And this is purely Java specific, but we can do this in almost any language that provides functional style of programming. So I'm going to use a collectors, which contains a toList method right here. And so if you look at this code right now, what did it do? It gets everyone whose name is, whose age is greater than 30, but got the name in uppercase. Now, would you agree this is beautiful when you look at this code? Well, there's a name for this. And Martin Fowler has a blog post. I encourage you to read this blog post. And his blog post is called Collection Pipeline Pattern. And this is what he calls it as, a blog post by Martin Fowler. And so take a look at this particular blog post. And he talks about the so-called collection pipeline pattern. So moving forward, we engage this collection pipeline pattern a lot more when you write code, and that becomes a lot more easier to express the code and makes it really elegant. So we can write beautiful code, we can write expressive code, and that's really, really nice, as you can see. Well, this is great so far. It is producing the result we wanted. Let's change the problem just a little bit, if you don't mind, before we go any further. Rather than getting the name in uppercase of all the people older than 30, let's change the problem just a little bit. I'm going to say get the name in uppercase of the first, so the first person older than 30. Now, if I say get the first person older than 30, what will you do? Let's go back and write this code in imperative style for a minute. So what would you do? You would say for person coming from create people, and then you would say if the person that is in here is dot get age is greater than 30, then what would you do? Hey, this is a first person whose age is greater than 30. I'm going to say over here, I will say string name is equal to null. How do you feel about this null? Null is a smell, isn't it? So you're like twitching your nose already. But then what do you do here? You say name is equal to person.getName dot to uppercase. And then you are going to put this in here as an uppercase value. And then when you're done with this, you're going to output the name, but only if the name exists. So you have to do the silly, if name is not equal to null, then you have to print it. Otherwise, what do you do? Else, you would say no one found. But you know this is not correct code yet, right? Because what am I missing? I need to do a break. This is in your control entirely. If you don't do the break, it is going to run off and get the wrong people and process everybody in the collection. That's not fun at all. But you have to take control of all of these things in the code. When I run this code now, it says Paula is the result. But look at the ugliness of this code already, right? Now, let's go ahead and rewrite this in functional style and see how it's going to look like. Well, in functional style, I'm going to say over here, again, output. We'll start with create people.stream, but this time filter, given a person.getAge is greater than 30, well, map and get the person's name. So we'll say get name is what I want to get out of this person, but I want to then convert it to a string to uppercase. Notice how the code is cohesive, one line doing just one thing at a time. And cohesion has software design values. If a code is cohesive, I can remove them easily. I can insert a new line easily. Try doing that in the other code, right? It becomes messy. But then what am I going to do now? I say dot find first, and or else I'm going to say no name. So I don't find anybody. I'm going to return a no name if I don't find anyone in this case. That also gave us Paula. But you look at this and say, aha, notice there is no break. That means we're in trouble, aren't we? Because we're going to take every single person, check what their age is, And anybody who is older than 30, get their name, convert to uppercase. And when we are done with all that hard work, we say, thank you. I want just the first one, throw everything else. How will you feel if you did all this work and the person getting the result says, thank you, but I just needed the first one. I didn't need everything else. You're going to just stare at them, right? Yeah, I did all this work and you threw it away, right? So this is one of the things extremely important to keep in mind. Elegance in the absence of efficiency has no value. This is something we got to keep in mind. Elegance in the absence of efficiency has no value. You cannot get by saying, look how charming it is. You still have to deliver the stuff. It doesn't matter that things are charming. We want performance, not at the expense of performance do we want elegance. So elegance in the absence of efficiency has no value. This is function composition. That is one of the most important things about functional programming is function composition. If somebody comes to you and says, do you like object-oriented programming? What would you say? Oh, I love it. But why do you like object-oriented programming? I'll tell you why I like object-oriented programming. I'll say polymorphism. So polymorphism is to object-oriented programming. This is really what we are really after. Why am I interested in object-oriented programming? It's polymorphism, because polymorphism gives me extensibility, right? That's what I get out of this. As function composition, and we'll come back and fill this in just a second, is to functional programming. And we'll see what that is in just a minute. So what is it that we're really after? Well, we definitely want this ability to do these function composition, but we don't want to process the data unnecessarily. So I go to person class now. In the person class, in the get age, I'm going to output get age for, and I'm going to put the name. Well, remember in the imperative style code we wrote, it starts processing, but the minute it finds Paula, it is going to break out of the loop. It would never touch Paul, Jack, and Jill. Well, that is efficiency, because once it finds the answer, it bails out. You don't want a functional style code naively to talk to every single object. But don't be mistaken. There are a lot of languages that give you functional style without the efficiency. They are just beautiful languages. But you try to put them through a large collection, they won't give you performance. But really, programming languages that are intended to be used as functional style for a large collection of data have to do more. And what is that more? Well, that more is what we're going to see here. When I run the code, notice what it just did. Here's a collection of people we have. It processed Sarah and Sarah. It processed Bob. It processed Paula. And the minute it processed Paula, it said, I am done. This is a very critical operation in functional programming, and that is called lazy evaluation. So laziness is fundamentally important. So what is laziness? On January the 15th, your boss calls you into the office and says, I've got a good news for you. You're going to work on this new project, and tells you everything about this project and says, we need you to finish this on April the 15th. And a final report and deliverable is due on April the 15th. So what do you do on January the 15th? You come out of the boss's office to your desk and you start on the project immediately, right? Of course not. I hear a few people scoffing over there. Absolutely. You will start on it promptly on April the 14th. In fact, there is something you know that the boss doesn't know. You know that you're going to quit on March the 1st. Why would you bother starting on this project, right? And what is that called? Efficiency, right? You don't do stuff until it becomes imminent. So what is the benefit of doing this? This is not a bad character. It is a good character. Why? Because you say, I'm going to put my time on the right priority. What is immediately due, I'm going to focus on. What is due at a later time, I'm going to postpone that. Now you know why in agile development, we do very short incremental cycles. Because if something is due in 7 months, I'm not going to touch it. But if something is due in 3 weeks, I better pay attention to it. And this is one of the reasons why that's how we work as humans, and that's called being efficient. Well, that's exactly what this code is doing right here. The code says, don't bother running this, be lazy about it. Because it was lazy, if it was not lazy, what would happen? If it was not lazy, it would have called upon every single person and said, what's your age? Which is a waste because we don't care about anyone's age other than until the first one we select. And similarly, we don't get the name, we don't transform to uppercase, we work efficiently only with people that matter, and the ones that are after, we don't touch it at all. That is laziness. Laziness gives us efficiency in functional programming. So, but there's one thing very important to keep in mind. You cannot get laziness without something else. Laziness is not possible without purity of functions. So this becomes extremely critical. When functions are not pure, you cannot get laziness. So that becomes extremely critical. Laziness is very, very important to achieve that. So purity is important. Why? Because if you're not going to favor purity, you cannot achieve laziness. Let me give you an example to illustrate that point. Let's go back to, again, a list of numbers 1 to 10, let's say. In this case, let's just keep it very small, 1, 2, 3. I want to take this code, I want to bring in a stream right here, and I'm going to say stream, and in this case, I'll create a stream of integer, let's say. In this case, I'll say stream is equal to numbers dot, and in this case, I'll say stream dot map, given an element, element times 2. And then once I do this, I'm going to say stream dot for each, and I'm going to simply print each one of them, system dot out and println, and I'm going to print these values out. Well, in this case, it's going to print the double of each of the values, so it did. But I'm going to now create an int factor is equal to 0, equal to 2. And I'm going to come in and put a factor right here. Notice this function right here. That lambda expression now depends on e, which is a parameter, but also depends on the factor, which is from the lexical scope. When I run this code, you can see it's still 2, 4, and 6. But what if I come in here and say factor equal to 0? That means this function is no longer pure. Why is it not pure? Because either it affects a variable outside or it's affected by a variable from the outside, and that's not acceptable. In fact, the Java language is trying to protect you. When I try to compile this code, Java says, oh no. It doesn't want you to compile the code. It says, don't do this. And Java says, if you do this, your code is going to fail miserably. Don't do this. And it's protecting you, right? But Java can only protect so much. It's not a purely functional language. So you know how some programmers are. They will roll up the sleeve and say, let me show you how to beat this. Very dangerous programmers. And so you go over here and say, int square bracket, and then you say new int square bracket 2. You write it like this. And then you put a square bracket 0 right here. What is Java going to do at this point? Java will not stop you. But if you look closely, the Java compiler will be shaking its head and asking the question, who are your parents? How did they bring you up, right? Because you're just doing all these kinds of stuff you should not do. Now notice what's going to happen. If I go back here and say factor square bracket 0 equal to 0, what is going to be the result? When I run this code, unfortunately, the result is all zeros. And that is because of lazy evaluation. The code becomes really hard to predict. It's not when you use the factor, but when you run the terminal operation in the end that it really evaluated it. To say the least, this can be confusing and source of bugs, but more important, you cannot be lazy in the evaluation. You're going to say, hurry up and do this. Why? Because I'm going to change it. Well, you cannot be lazy if a value is going to be mutated along the way. So laziness and mutability don't go together. So now you know why functional programming emphasizes immutability. The reason they emphasize immutability is not because it's fashionable. Telling programmers they should favor immutability is like telling children they should eat vegetables. Nobody wants to. It's like, why? And so we have to really motivate and say, here is the reason. Because in functional set of programming, we got elegance. But we cannot live with elegance. We want efficiency too. But if we want elegance with efficiency, we need to bring in laziness. If you want laziness, we need immutability. So there's a really good technical underpinning for these principles and practices. So, okay, great. We're going to be lazy. We're going to make the code really elegant and expressive. We're going to make it efficient. This is all great. How is it practically possible to do this? So this is my design concern. How could I, in a language like Java and C# and JavaScript and Python and Ruby and Smalltalk and all these languages, how could I build with immutability? How many of us program in language like Haskell? There are a few people who do, who have that ability to sit and program in a purely functional language. For the rest of us, we live in the bazaars. We live everywhere action happens. Stuff happens. You step on stuff and say, what did I step on? That's the life we live in. And how do you bring in purity in that world we live in? Well, the first thing to keep in mind is, what does it mean by functional purity? Well, here's a way to think about purity. I'm sure everyone will agree to the first definition. Well, first of all, before that, pure function, what is one of the advantages? Will always give you the same output for the same input. That predictability is one of the traits of pure functions. They have no side effects. This is one of the really beautiful things about pure functions. They have no side effects, right? So the pure functions do not have any side effects. But let's talk about what pure functions really do. So rules, I'm going to say two rules for purity. And most of us will immediately agree to rule 1. But rule 2 is equally important, if not more. Rule 1, the first rule is the function does not change any value. This is the first rule, isn't it? If you want to write a pure function, it doesn't change any value. And everybody's like, yeah, of course. But that's not enough. This is a necessary condition, but not sufficient condition. The second condition is the function does not depend on anything that may possibly change. The second rule is extremely important for functional purity. The example I just showed you a minute ago, where I am setting the factor as an array. Remember that lambda? That lambda did not change anything. So it follows rule number 1, but it does not follow rule number 2. It is depending on a variable that possibly changes. In fact, in this case, it does change. So that function is not pure because of rule number 2. But that's dangerous because when a value can change outside, that execution within the lambda cannot be lazy. You're going to say, did I execute this before the change, or after the change, or even worse, during the change? That's when we get the concurrency issues and race conditions, isn't it? So the functions have to be really, really pure. That is one of the first rules, tenets of functional programming. But how is it practical to implement immutability? We write code where we mutate state. We change everything we can think of. How in the world can we really live practically with immutability? And the answer to that question is, we can do this by rethinking about our design. I'm talking about languages like Java and C# and JavaScript, where we mutate everything every corner we turn. What do we do about it? I want you to think of the so-called circle of purity and a thin ring of impurity around it. So if you remember, imagine a ring, and imagine that circle is absolutely pure. Once you enter the circle, you don't change anything. That's a circle of purity. And once you're in the circle, you don't mutate anything. Then when you leave the circle, on the thin ring, you can do all the mutations you want. Here's a way to think about it slightly differently. Remember, we are dealing with the so-called functional pipelines. And when you get to a functional pipeline, the functional pipeline may engage laziness in its evaluation. So what you want to do is think about the functional pipeline as your circle. And what you want to do is, before you enter that circle, if you will, so if you consider this here, before you enter that circle, you might do impurity. So in this case, I have this function composition that I'm going to work with, And in this function composition, what I want to do is take on that particular pipeline right there. And in this pipeline, before I enter the pipeline, I could perform the mutations. But once I enter it, I shouldn't do any mutation until I leave it. So here's another way to think about it. Imagine there is a fast-moving train. So here's my train. So the train is going to be running across stations. Now the very first question is, do you recommend that somebody should enter the train? And the answer is, of course. If nobody enters the train, what's the purpose of a train? Do you think somebody should exit the train? I hope so. That's a good thing too. So it's perfectly okay to enter a train, perfectly okay to exit a train, but never when the train is in motion. So when the train is moving, don't try to enter. More important, don't try to exit. So you definitely want to consider when to enter and when to exit. So think of a train in motion as a pipeline. Before you start, enter, make changes. While it's in motion, don't make any change. Once you hit the terminal operation, feel free to make any changes you have to. So as long as you can preserve that region boundaries, you can safely start designing systems to make use of this. So be very sensitive to mutations within function pipeline. So to think functionally, what are the things we need to think about? To think about this, think about how do you design the system around immutability and how to frame things around this immutability, leverage functional pipeline, leverage laziness. But that brings one other problem. What about exceptions? Well, exception handling is always painful, but it's even more painful in functional programming. In the imperative mindset, what do? In the imperative mindset, you say, if something goes wrong, blow up. Right? That's what you do. You're walking. You hit your toe, mom, and you run back. Well, that's basically what imperative style mindset is. But what about in functional programming? In functional programming, you deal with what is called streams of data processing. That is the pipeline, isn't it? So when you deal with the pipeline, there is upstream and then there is the downstream. So you are flowing through the stream and you are coming down to this downstream. Now let's say something goes wrong right there. What do you do when something goes wrong right there? Well, here's the way to think about it. Imagine you're driving on the freeway. You are 2 kilometers before you have to exit when you have a flat tire. What's the most illogical thing for me to tell you? Oh, you have a flat tire, drive in reverse. That doesn't make any sense. What you do is you exit safely to the nearest exit, right? So in other words, you always deal with things downstream. You never go upstream. And so if something goes wrong here, what do? Very simple answer. Treat error as data and deal with it downstream. And this is one of the most important things to keep in mind when it comes to exception handling. When you deal with exceptions, you don't blow up. Instead, you say, whoops, something went wrong here, convert it to data, to error, treat error as data, and go downstream and handle it. That is one of the most important things to keep in mind, is you don't blow up. Exception handling and functional programming are not orthogonal. They are something you never mix together. The other day I saw on the news, there was this lady. She decided to smoke. Okay, people smoke. She decided to have a big container of gasoline. People have gasoline. But she decided to have it next to her and smoke. Things didn't go well. No wonder, right? So these things don't work together. There's a reason why we say, no fire, no smoking here. There's a reason for it. And that's exactly the point here, is we don't mix fire and oil together. It doesn't go well. Functional programming and exception handling don't exist together. Makes no sense. So we need to take the error, treat it as a data, and deal with it downstream. That brings up the question, what does Java 8 streams do? I will summarize what Java 8 streams do for exception handling in 2 words. And those words are called good luck. That's it. Java 8 stream says good luck. We don't have an answer for you. You're on your own for this. And then they look at you and say, did you say exception? Right? Because it doesn't go together. This is where things like JavaScript promises come in. This is where Java's completable future comes in. Both promises in JavaScript, uncompletable future, what do? They have two tracks. They have a data track and they have an error track. The data hops to the data track and the error hops to the error track. So you treat error as if it's data downstream. So look at promises in JavaScript. Hey, but promises and completable future in Java both deal with 0 or 1 piece of data or 1 piece of error. But I want the stream of data being pushed towards me. How could I possibly handle a stream of data? This is the clear distinction between these two. This is where reactive programming's observable come in. And this was an aha moment for my realization to realize that reactive programming is not a completely disjoint concept. Reactive programming is a very logical step from functional programming. In functional programming, we talk about the so-called function composition and lazy evaluation. Reactive programming starts right there. So let's talk about the differences between these two. When you look at promises, if you will, so if you look at the promises, or what is the other one in Java, the completable future, right? So promise and completable future deal with 0 or 1 data. Observable, on the other hand, what do? The observables deal with 0 or more data. That's one of the biggest distinctions between them. This is 0 or more. In the case of this, there are two channels. What are the two channels? A data channel and an error channel. That is what a completable future or promise has. What about the observables? Observables have 3 channels. What are those? Well, you know what the first two are already. There's a data channel through which data comes out. They also have what is called an error channel through which an error comes out, potentially. And there's a third one, which is your complete channel, where you get a signal saying that this is complete, and you're not going to get any more response from it. So this is one of the biggest distinctions between these two ideas. So streams in Java are a limited case of observables in reactive programming. So as you start playing with the functional ideas, if you feel that exception handling is a barrier, you can look at something like observable, where they treat error as a first-class citizen. They don't kind of say, oh, hush, hush, don't talk about errors. They actually say, life happens. You know, the worst thing we ever did as a field is calling exceptions as exceptions. We should have called it normal, because stuff happens and we have to just deal with it, right? And that is one of the biggest things here, is that we should deal with these as first-class citizens. And so in true functional programming, we don't treat exceptions as anything other than another form of data. And we deal with it downstream rather than blowing up and saying we can't handle it. So when it comes to designing functional systems, we have to rethink the way we do this. We should draw the functional pipeline, engage lazy evaluation, engage composition, but more important, begin to deal with error and treat it with respect. And error as a first-class citizen, take the error downstream and deal with it, and be able to process data, process error, and then effectively implement the pipeline. And while doing it, honor the immutability that is extremely important for all this to come together and work together. So we can practically design functional systems if we can pay attention to some of those details. I'm not saying it's easy to do in languages like Java or C# or JavaScript, but it's not also impossible to do if we were to pay attention to some of these very important technical underpinnings. Hope that was useful. Thank you.
Maybe someone has some questions?
Oh, please, fire away.
Okay, anyway, thank you.
Thank you.